In this lecture, we're going to look at partial correlation, a very close cousin of the semi-partial correlation we worked through in the last lecture. They look almost identical on paper, but they answer slightly different questions. By the end of this lecture, you'll know exactly how partial correlation differs, how to compute it, and when you want to try using it. Now, the key difference between partial and semi-partial correlation is that partial correlation removes x2's influence from both y and x1, not just x1. And because of that extra cleaning step, the partial correlation is usually larger in magnitude than the semi-partial correlation. Now let's look into both of those ideas. In the previous lecture, we worked with three correlations. We have r between y and x1 of 0.7, r between y and x2 of 0.6, and r between x1 and x2 of 0.5. The semi-partial correlation removes x2's influence from x1 only. Y is left untouched. So in that example, SR1 came out to be 0.4619 and SR2 came out to be 0.2887. Keep those two numbers in mind because we're about to recompute them as partial correlations, and I'll show you what changes. Here are the two formulas side by side. On the left side is the semi-partial. We subtract the shared piece in the numerator, and the denominator has a single 1 minus r12 squared factor. On the right is the partial. Notice the numerator is exactly the same. The only difference is in the denominator. The partial has an extra 1 minus r y2 squared factor. That extra factor is always less than or equal to 1, so dividing by its square root makes the fraction bigger. That's the whole story of why partial is usually bigger than semi-partial. You have the same thing on the top and a smaller thing in the denominator. Here is a visualization that will hopefully make a bit more sense. On the left, in the semi-partial, we take x1 and scrub x2's contribution out of it. The trimmed x1 is the gray circle, but y is left untouched. It's still the full teal circle. The semi-partial is the remaining overlap between the trimmed x1 and the full y. On the right, the partial, we do the same scrubbing to x1, but now we also scrub x2's contribution out of y. Both of those circles are gray. The partial correlation is the overlap between trimmed x1 and trimmed y. So that's the key distinction here. Partial cleans both sides, semi-partial cleans only one. So let's walk through that formula one more time. The top is the same numerator we had for the semi-partial, the raw correlation between y and x1 minus the product ry2 times r12. That numerator is the unique portion of x1's relationship with y. The denominator is where the partial differs. We divide by the square root of 1 minus r12 squared times 1 minus ry2 squared. Since ry2 squared is positive, the factor 1 minus ry2 squared is less than 1, so it shrinks the denominator and grows the fraction. That's the algebraic reason partial is larger than semi-partial whenever y and x2 are correlated at all. So now let's plug in our running example here. ry1 is 0.7, ry2 is 0.60, and r12 is 0.50. So our numerator is 0.70 minus 0.60 times 0.50, which is 0.70 minus 0.30, which is equal to 0.40. Our denominator is 1 minus 0.60 squared is 1 minus 0.36, which is 0.64. 1 minus 0.50 squared is 0.75. If you multiply those, we have 0.64 times 0.75, giving us 0.48. We then take the square root to get 0.6928. We then divide that by 0.40 to get 0.5774. That is our partial correlation PR1. Notice it's comfortably bigger than the semi-partial SR1, which was only 0.4619. Now we can do the same thing for x2. So our numerator swaps. It's now 0.60 minus 0.70 times 0.50, which is 0.50 minus 0.35, which is equal to 0.25. And the denominator is 1 minus 0.70 squared, which is 1 minus 0.49, which is 0.51. 1 minus 0.50 squared is still 0.75. We multiply those, 0.51 times 0.75 to get 0.3825. The square root of that is 0.6185, and then we divide by 0.25 to get our final result of 0.4042. That's PR2, which is again bigger than the semi-partial SR2, which was only 0.2887. Here is a comparison in one place. For x1, the semi-partial was 0.4619, and the partial is 0.5774, a noticeable jump. For x2, the semi-partial was 0.2887, and the partial was 0.4042. In relative terms, an even bigger jump. So the general pattern is partial is always at least as large in magnitude as the semi-partial, and the gap grows more strongly the more the other variables correlate with y. So which one should you use? How do you pick between them? It really depends on the question you're asking. So reach for semi-partial when you want to know how much of y's total variance is uniquely explained by x1. Most regression software calls this the part correlation. And if you square it, you get the increment in r squared when you add x1 to the model. It is the natural companion to r squared. Reach for partial when you want to describe the correlation between x1 and y after statistically controlling for x2. That language, controlling for x2, is really common in things like medicine, where researchers talk about adjusting for confounding variables. These are both useful, they just emphasize different sides of the same picture. So to recap what we've learned here, partial correlation strips x2 out of both y and x1, whereas semi-partial strips it out of x1 only. Algebraically, they share the same numerator, but the partial has an extra 1 minus ry2 squared term in the denominator, which makes the partial larger whenever y and x2 have any relation to each other. So here's a rule of thumb. When your mental model is r squared and explained variance, think about SR squared. When your mental model is about controlling for a confounding variable, think about PR. Same math, just a different emphasis. One last thing before we move on. Both of the tools we just learned, semi-partial and partial, depend on how correlated your predictors are with each other. In our example, R12 was just a modest 0.50 and everything behaved nicely. But when predictors get very highly correlated, something called multicollinearity kicks in, and both of those quantities start to behave badly. That's what we'll dig into in the next lecture, what multicollinearity actually is, why it matters, and how to spot it. I'll see you there.